an EMF to be induced in a circuit, a current to be induced in a circuit. To be induced in a circuit, brother, kindly change the magnetic flux linked with it. So these two laws formulated by Faraday, Michael Faraday, the magnitude, or you can say component of magnetic field along the normal and area of the element. If the magnet is moved with great speed towards the coil, the advantage, the informative source from Faraday's second law is that hello students, this is our second session on the topic electromagnetic induction. What did we learn in that previous session? So we understood the physical meaning of a very beautiful phenomenon called electromagnetic induction. What was the meaning? It was nothing but inducing an EMF and hence inducing some current in a closed coil, in a closed circuit. How? By changing the magnetic flux linked with it. So, what was the basic inference we got? The basic inference we got was whenever a closed coil is subjected to varying magnetic fields, changing magnetic fields, an EMF and current is induced in it. And we also demonstrated two experiments, coil magnet experiment and coil experiment, to understand the phenomenon. What is that we are learning in today's class? A very important topic called magnetic flux. Because only when magnetic flux is changed, magnetic field strength is changed, EMF is induced. So my primary observation is to understand what is magnetic flux, and thereafter understand a very important law called Faraday's laws, which justifies electromagnetic induction. Therefore now, the first thing that we study in today's session is the concept of magnetic flux. Many 1 mark riders, 1 mark questions are asked from this topic of magnetic flux. Makla, ನಾವು ಎಲೆಕ್ಟ್ರೋಸ್ಟಾಟಿಕ್ಸ್ ಓದಿದಾಗ ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸ್ ಅನ್ನೋ ಕಾನ್ಸೆಪ್ಟನ್ನು ಕಲಿತ್ವಿ. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಅನ್ನೋದು ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸಿಗೆ ಸಮನಾಗಿರೋ ಒಂದು ಕಾನ್ಸೆಪ್ಟ್. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ is similar to something called electric flux, but defined with respect to magnetic field. So now let us try to understand what is magnetic flux. Now, I'll consider a surface of area A. So, I have considered an area element, some surface of area A, area element ಅಂತ ಕರೆದೆ. B is the magnetic field acting radial to the surface, tangential to the surface. So what does B represent? Magnetic field strength. E represents electric field strength. B represents magnetic field strength. So B is the magnetic field which acts radial to the given surface. Now what do? I draw a normal n cap to the given surface. So n cap is the normal that is drawn to the surface. And what is the component of magnetic field along the normal? Al electric flux nodidvalva cos theta anta. Similarly, B cos theta is the component of magnetic field along the normal. So these are my initial considerations. And surface area A, a surface element of area A. B, magnetic field acting radially or tangentially to the given surface. N is the normal, where B cos theta is the component of magnetic field acting along the normal. What is theta? Angle between the normal and magnetic field. Now, the magnetic flux through the surface is given by phi B is equal to B cos theta into ds. ನೆನಪಿದ್ರೆ electric flux across a given surface is E cos theta into ds. If you analyze back, the electric flux through any given surface is E cos theta into ds. ಏನು ಹೇಳಿದ್ವಿ ಅದನ್ನ? Product of component of electric intensity along the normal and the area of the element was called electric flux. Similarly, magnetic flux is B cos theta into A. Again a product. It is the product of the magnetic field along the normal. Component of the magnetic field along the normal and the area of the given surface is called magnetic flux. So what was magnetic flux, students? It was nothing but B cos theta into A. What was B cos theta? Component of the magnetic field along the normal. What was A? Area of the surface. Their product is called as magnetic flux. Since it is dot product, we also write phi equals vector B dot vector A. Now, what is the SI unit of magnetic flux? Many a times it is asked as 1 mark question. The SI unit of magnetic flux is Weber. Keep in mind, very important, the SI unit of magnetic flux is Weber. And we say 1 Weber is 1 Tesla into 1 meter square. ದಯವಿಟ್ಟು ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ, ಯೂನಿಟ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇಸ್ ಟೆಸ್ಲಾ. Magnetic flux is Weber. Usually you get confused and lose marks there. Magnetic field is Tesla. Magnetic flux is Weber. So what is magnetic flux? B cos theta into A. Product of the magnitude, or you can say component of magnetic field along the normal, and area of the element is called magnetic flux. Therefore, in simple terms, if I need to analyze, magnetic flux is nothing but number of magnetic lines of force. Electric lines ಓದಿದಿರಲ್ವಾ, ಆ ಥರನೇ magnetic lines of force which pass normally through the area. How many magnetic lines of force pass normally through that area is what we call magnetic flux. B cos theta into A. So in simple terms, what I want you all to understand is magnetic flux is nothing but number of magnetic field lines. The total magnetic field lines passing normally through a given area, and mathematically it is B cos theta into A with SI unit Weber. Fine. Now we go to a very, very important set of laws, something called Faraday's laws on electromagnetic induction. Actually a set of laws which will justify the phenomenon of EMI, which is often asked for 2 marks. Faraday's laws of EMI. Why is it called laws? Because there are 2 laws, first one and second one. So these 2 laws formulated by Faraday, Michael Faraday, is what we study as Faraday's laws. The first one, it is actually the definition of EMI again. The first law says, whenever magnetic flux linked with the circuit changes, EMF is induced in it. ಆಗಲೇ ಕಲ್ತಿದ್ದೀವಿ. If I want an EMF to be induced in a circuit, a current to be induced in a circuit, magnetic flux linked with it has to be changed. That is what the first law also says. Whenever magnetic flux linked with the circuit changes, EMF is induced in it. I can induce an EMF in a circuit only when magnetic flux linked with it changes. Further it says, this induced EMF will last long until the change in the magnetic flux continues. The second part is very beautiful. It says, this induced EMF will last long. The EMF induced in the circuit will continue to exist only until the change in the magnetic flux continues. Only until there is change in magnetic flux, the EMF induced in the circuit will exist. The moment there is no change in the magnetic flux, there is no induced EMF and no current induced in the circuit. So beautifully the law says, if you want an EMF to be induced in the circuit, change the magnetic flux linked with it. And if at all this EMF has to be present in that circuit, you have to change the magnetic flux present. If the magnetic flux does not change, there will be no continuation of induced EMF. So very clearly he says, whenever magnetic flux linked with the circuit changes, only then EMF is induced in the circuit. If you want an EMF to be induced in a circuit, brother, kindly change the magnetic flux linked with it. How to change the magnetic flux? In my previous session, I've already worked on the coil magnet experiment or the coil experiment, several other techniques in the next. But what is primarily needed? If I want an EMF in the circuit, if I want a current in the circuit, no other option. If you have to induce that, change the magnetic flux linked with it. And this induced EMF, how long will it exist in the circuit? Until you keep on changing the magnetic flux. Once you don't change the magnetic flux linked with the circuit, the existence of EMF is done. So very clearly, this induced EMF will last long until the change in the magnetic flux continues. Good. Coming to the second law. Okay, fine. In your first law you have told, change the magnetic flux, EMF is induced. I will do. But how much of EMF is induced? I change the magnetic flux. How much of EMF is induced in the circuit? Therefore, Faraday says, the magnitude, the amount of induced EMF in any circuit, the amount of induced EMF is directly proportional. It is directly proportional to the rate of change of magnetic flux linked with it. So mathematically I write E is proportional to d phi by dt. Change in magnetic flux with respect to time is directly proportional to induced EMF. The magnitude of the induced EMF depends upon the rate of change of magnetic flux, which means if the magnetic flux changes by a higher order, the induced EMF will be more. If the magnetic flux changes by a lower order, small amount, the amount of EMF induced is also small. Andre, if the magnet is moved with great speed towards the coil, magnetic flux changes by higher amount. Speed of the magnet is more. Induced EMF is more. If you move the magnet slowly towards the coil, magnetic field changes by a small amount so that induced EMF is less. So very clearly, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with it. Therefore, very clearly, students, the advantage, the informative source from Faraday's second law is that it gives the strength of the EMF induced in a circuit. What is the actual EMF that is induced in the circuit? How much of EMF is induced in a circuit is given by Faraday's second law. But it also has a limitation. What was the limitation? It does not give the direction of the induced EMF. Faraday's second law does not give the direction of the induced EMF. It just gives the strength or magnitude of the induced EMF. So my dear students, here we clearly come to understand Faraday's laws, which justifies the phenomenon of EMI. In my next session, what Mr. Faraday couldn't do, I will take it up with the help of Mr. Lenz. We will try to understand the direction of the induced EMF, rate of change of magnetic flux gives the magnitude of induced EMF according to Mr. Faraday. Until we meet up in the next session, have a good time. Thank you.